Okay, so continuing with this chapter of relativistic dynamics, we will continue talking about collisions, elastic and non-elastic collisions. So to begin with elastic collisions, I will explain elastic collisions through some examples, especially. I will begin with this example. We will consider two masses M1 and M2 in R, and the frame R. So before collisions, they have the two momentums, 3D momentums, P1 and P2, and of course, energies E1 and E2. When they do this collision, so their momentums will be P prime 1 and P prime 2 as a 3D momentums, and E prime 1 and E prime 2 as the energies after collision. If we go to R star and just remember that R star is the frame attached to the center of mass. In this frame R star, you know that by definition, the sum of momentums of 3D momentums is 0. So P1 star plus P2 star is equal to P prime 1 star plus P prime 2 star, which is equal to always 0 in R star. So if you take the first one, P1 star plus P2 star equals 0, so P1 star is equal to minus P2 star. So P1 star squared is equal to P2 squared. Then if you multiply by C squared, then P1 star squared C squared is equal to P2 star squared C squared. And if you remember from last time, we found that E squared is equal to P squared C squared plus M squared C to the power 4, which is also applicable to quantities in R star. So P squared C squared should be equal to E squared minus M squared C4. So P star squared C squared should also be equal to E star squared minus M squared C4. So if you replace P squared C squared by this value according to the energy, so P1 star squared C squared is E1 star squared minus M1 squared C4, which is equal to P2 squared C squared is replaced by E2 star squared minus M2 squared C4. This is equation number 1. So keep in mind this equation number 1, we will need it later. Okay, if you take the second part of the equation, P prime star, P prime 1 star should be equal to minus P prime 2 star. So also the same calculation. We multiply by C squared, we replace by the value according to the energy. So E prime 1 star squared minus M1 squared C4 is equal to E prime 2 star squared minus M2 squared C4. This is equation number 2. So we have equation 1 and equation 2. From equation 1, we can rewrite the equation number 1 in terms of energies at the left-hand side, and the rest is on the right-hand side. So E1 star squared minus E2 star squared is equal to M1 squared minus M2 squared times C4, and equation number 2 becomes E1 prime star squared minus E2 prime star squared is equal to M1 squared minus M2 squared as a common factor times C4. So you see these two quantities are equal. So these quantities are equal. So we have E1 star squared minus E2 star squared. that is equal to E1 prime star squared minus E2 prime star squared. So this equation is equation number 3. The conservation of energy tells us that NR star, when applied NR star, it will tells us that E1 star plus E2 star is equal to E1 prime star plus E2 prime star. This is equation number 4. If you consider the equation number 4 with equation number 3 in the previous slide, and you divide equation 3 by equation 4, so we have E1 star squared minus E2 star squared over E1 star plus E2 star, that is equal to E1 prime star squared minus E2 prime star squared divided by E1 prime star plus E2 prime star. So here on the numerator you have a subtraction of two squared quantities, so this becomes E1 star minus E2 star times E1 star plus E2 star. The same for this quantity, so we have E1 prime star minus E2 prime star times E1 prime star plus E2 prime star. So you can remove the E1 plus E2, the E1 plus E2 thing. So you remove the pluses quantities and you will get this equation E1 star minus E2 star, that is equal to E1 prime star minus E2 prime star. So if you add this equation, let's say this is equation number 5. If you add this equation to equation number 4, so you get 2E1 star, that is equal to 2E1 prime star. And if you subtract 3 from 4, you get E2 star is equal to E prime star. So you see that the energies in R star are conserved, and only in R star. This is not applicable in any other frame. Only in R star, each particle conserves the same energy in R star. So the energy E1 star before collision is equal to E1 prime star after collision for particle number 1 in R star. And E2 star is equal to E2 prime star, the energy of particle number 2 in R star before and after collision. So particles will have the same energy in R star before and after collision. Okay, so let's go for the Compton effect. One consequence or one example of elastic collision, of an elastic collision that you probably know about it, is the Compton effect. Compton effect is realized when we use a light metal with an X-ray beam. So X-ray is diffused by the electrons of the metal. X-ray is diffused at an angle theta at a frequency less than the incident frequency. Less than the incident frequency. And while electrons are diffused at an angle phi. This phenomenon was discovered by Compton in 1923. Why do we use light metals? Because we need weakly bonded electrons. So the bond is very weak in light metals. So the electron is supposed free. So it's like you are working with free electrons that are initially at rest. Why do we consider them at rest? Because you know electrons circulates around the nucleus of their atoms. They circulate around a point that is the nucleus of the atom. So with respect to an X-ray that is coming from far away with respect to the atom, so the X-ray will see the electron as if it was rotating around itself in the same position. So it's like an electron at rest, approximately at rest. So this is a collision between an elastic collision between a photon and an electron. Why is it elastic? Because before collision we have a photon and an electron, and after collision we have the same two things, a photon and an electron. Okay, so we have an X-ray with an energy E1 h nu or hf, whatever you name the frequency, and the electron that is initially at rest, a free electron at rest. Let's suppose x is the initial direction of X-rays. So an X-ray collides with an electron. The X-ray is diffused through this angle theta with a new energy E prime 1 that is equal to h nu prime, the new frequency that is less than the initial frequency, and the electron is ejected through the angle phi with some speed, and we will see how the electron gets this energy and this speed. Okay, first let us use conservation of energies. So before collision, we have a total energy of E1 plus E2. So number 1 corresponds to the photon, number 2 corresponds to the electron. So E1 plus E2 before collision is equal to E prime 1 plus E prime 2 after collision. E1 is h nu, E2 is an electron at rest, so we consider its rest energy mc squared. E prime 1 is h nu prime, the new frequency of the photon, plus E prime 2, the new energy of the ejected electron. This is the unknown. So E prime 2 is equal to h times nu minus nu prime plus mc squared. This is equation number 1. So we have to keep this equation because we need it to continue with the study of this Compton effect. Okay, the second conservation is the conservation of momentum. So P1 plus P2 is equal to P prime plus P prime 2 before and after collision. So we should have P's here. So P1 plus P2 before collision is equal to the total momentum after collision, which is P prime 1 plus P prime 2. So we put the terms corresponding to 1 on this side, the terms corresponding to 2, which is the electron, on the other side. So just add some p's here. So P1 minus P prime 1 is equal to P2 minus P prime 2, and we square the equation. So P1 minus P prime 1 squared is equal to P2 minus P prime 2 squared, etc. You develop this equation. So P1 squared plus P prime 1 squared minus 2 P1 P prime 1 is equal to P2 squared plus P prime 2 squared minus 2 P2 P prime 2. And you know that P squared is invariant. P squared for any particle is equal to m squared c squared. No matter the velocity, whatever the velocity is, whatever the motion is, whatever the conditions, P squared, which is the norm of for momentum, is always equal to m squared c squared. So for a photon, it's 0 because m is 0. So this quantity is equal to 0, this quantity is equal to 0. The equation becomes minus 2 p1 p prime 2, that is equal to p squared for an electron before or after collision. It's the same. P squared is always the same. So it's m squared c squared plus m squared c squared because it's the same electron. So it's 2m squared c squared minus 2 p2 p prime 2. So you can multiply by a minus, you remove the number 2, and you get p prime p1 times p prime 1 equals p2 prime minus m squared c squared. So this is equation number 2. We have in this equation two unknowns, p1 p prime 1 and p2 p prime 2, two scalar products. So let us find these two scalar products for 1, which is the photon, and 2, which is the electron. Okay, so we put in front of us the 4 vectors before and after collision. So P1 before collision, it is the X-ray going through the x-axis. So we have h nu over c. Here we are using the c, not the c equals 1. We will consider the c. So h nu over c along x, and 0, 0 along y and z, and P10, it has the same magnitude h nu over c. And for the electron, P2, the electron is initially at rest, so it's 0, 0, 0 in space. And we have the energy E2 over C because C is different from 1. So E2 over C, and here E2 is the rest energy, which is mc squared. And after collision, we have the new momentums. For the photon, it's p prime 1, it's h nu prime over c times cosine theta, because it is diffused at an angle theta with x, and along y, it's h nu prime over c sine theta, no magnitudes over c, it's over z, it's 0, and the time coordinate is h nu prime over c. For the electron, it's p prime 2, whatever the momentum, the 3D momentum of the electron, cosine phi over x, p prime 2 sine phi over y, 0 over z, and e prime 2 over c. So we need p1 times p prime 1 and p2 times p prime 2. If you multiply p1 by p prime 1, so we begin by the time coordinates, so it's h squared nu prime over c squared minus the space coordinates, so it's h squared nu prime over c squared cosine theta. So it's equal to, we have a common factor that is h squared nu prime over c squared times 1 minus cosine theta. This is P1, P prime 1, and P2, P prime 2. So we have to only consider time coordinates because we have zeros here in space. So here we are multiplying by a 0. So we just have P2 times E prime 2 over C squared. So this is P2 times P prime 2. We replace it in this equation. So we replace these values in equation number 2. We replace in 2. So h squared, this is P1 times P prime 1. So h squared nu prime over c squared by 1 minus cosine theta is equal to P2 times P prime 2, so it's E2 E prime 2 over C squared minus the rest of the equation, M squared C squared. Okay, E2 is the energy, is the rest energy before collision, so it's MC squared E prime 2 over C squared minus M squared C squared. Okay, we can simplify by C squared here, so it's equal to M E prime squared minus M squared C squared. So if you remember equation number 1, we found an expression for E prime 2. So let's replace E prime 2 by its value that was found in equation 1. So H squared nu prime over C squared 1 minus cosine theta is equal to M times E prime squared 2, so it's M H nu minus nu prime plus M times MC squared, so plus M squared C squared minus this quantity M squared C squared. So you have here M squared C squared minus M squared C squared. So H squared nu prime over C squared 1 minus cosine theta is equal to MH nu minus nu prime. Okay. So now we need to find the new energy H nu prime as a function of the initial energy H nu. So we use this equation and we continue our calculations using this form of the equation, 1 minus cosine theta H nu over C times H nu prime over C, that is equal to MH nu minus MH nu prime. We put H nu prime as a common factor, so we have 1 minus cosine theta H nu over C squared plus M on this side, that is equal to MH nu. So H nu prime is equal to MH nu over 1 minus cosine H nu over C squared plus M. And if you divide by the mass, so H nu prime is equal to H nu over 1 minus cosine theta times H nu over MC squared plus 1. Okay, so the cosine is always less than 1. Here we have a 1 plus something, so the denominator is always greater than 1. So H nu prime is less than H nu. And this is not strange because a diffused electron normally has less energy than the initial electron. So this is verified, mathematically verified by this equation. You see that H nu prime is less than H nu according to this equation. So diffused electron have less energies than incident, diffused photons have less energy than incident photons, and this difference of energy is obviously transferred to the electron. So it's the electron who is taking this this difference of energy. So the same equation, if we use the same equation, so H nu over 1 minus cosine, etc., minus H nu prime is equal to 0 because these two quantities are equal. So if you make the common denominator, so H nu minus H nu prime times the denominator over the denominator is equal to 0. So we have this numerator that is equal to 0. So H nu minus H squared nu prime over MC squared plus H squared nu prime over MC squared cosine theta minus H nu prime is equal to 0. You can simplify by an H. So nu minus h nu prime over mc squared plus h nu prime over mc squared cosine zeta minus nu prime is equal to 0. So we have this difference of frequency, nu minus nu prime, that is equal to h nu prime over mc squared times 1 minus cosine zeta. So this is our delta nu, the difference of the frequency of the photon, but before and after collision. So the difference of frequency after the collision with the electron is equal to this quantity, and h times this delta nu corresponds to the energy that will be transferred to the electron. Also, we can write it in as a function of lambda, the wavelengths, because lambda is equal to c over nu. So lambda is equal to c over nu, and lambda prime is equal to c over lambda prime. So c over lambda minus c over lambda prime is equal to h over mc lambda lambda prime times 1 minus cosine zeta. So you can find your lambda minus lambda prime, which is delta lambda's difference of wavelengths during this collision, which is equal to h over mc times 1 minus cosine zeta. This is the difference of the wavelengths after the collision between the incident photon and the diffused photon. This quantity h over mc is called the Compton wavelength, and you can calculate it numerically. Lambda c or lambda Compton, which is h over mc. H is the Planck's constant, m is the mass of the electron, c is the speed of light. So you have all these numbers. So lambda c is equal to 0.0242 angstrom. Angstrom, you know, it's 10 to minus 10 meter. So you can see that delta lambda is maximum if zeta is equal to zeta here, delta lambda. So when zeta is equal to pi, so the cosine is equal to minus 1, so delta lambda becomes 2hc over mc, or 2 lambda c, 2 lambda Compton, 2 Compton wavelengths. And if you go back to the equation with nu and u prime, delta nu here, you see that if zeta is equal to 0, then h nu is equal to h nu prime. Delta nu is equal to 0. So we have no transfer of energy. The photon continues its trajectory on a straight line. It is not diffused. It does not interact with the electron. So we have no transfer of energy. The electron stays the same. The photon continues on a straight line as if nothing happens to it. So we have no transfer of energy in this case. And if zeta is equal to pi, so h nu prime will become h nu over 2 h nu over mc squared plus 1. This is the maximum transfer of energy to the electron. So in this case, we have a maximum energy transfer to the electron. So it's when the photon loses the most of energy. So the photon does not disappear because in a Compton effect, the photon is never totally absorbed. So even with this maximum transfer of energy, h nu prime is not 0. So in a Compton effect, the photon is never totally absorbed by the electron. So we always have h nu prime that is different from zero. But when theta is equal to pi, and we have a maximum transfer of energy, this would be our least h nu prime, our smaller energy of the diffused electron. Okay, so this is the variation of delta lambda as a function of theta between 0 and 2 pi. Of course, for the electron, you have a maximum of energy when theta is equal to pi at a wavelength of 2 lambda c. And for the photon, suppose this is the initial energy of the photon. So the maximum loss of energy is for theta equals pi. So if it's like we are mirroring the same variation. So the red one is a mirror of the blue one or the black one because they have opposite behaviors. So when the electron gains energy, the photon loses energy. And this difference of energy is transformed into a kinetic energy of the electron. So the energy comes out at with a certain velocity, so with some kinetic energy that is equal to h delta nu, or h times nu minus nu prime. Okay, so now we will see the relation between theta and phi. Going back to the conservation of momentums, P1 plus P2, that is equal to P prime plus P prime 2. If you take the projections of this equation along x and y, so initially P1 is the photon h nu over c along x, and the electron is at rest, so this is 0. That is equal to, after collision, when you have a diffused photon, so it's h nu prime over c cosine theta plus p prime 2 cosine phi over the axis x. So these are the projections on x. And on y, initially we have no momentums along y because the electron is at rest, the photon is along x, so no momentums along y before collision. But after collision, after the diffusion, we have the momentum of the photon, which is h nu prime over c sine theta plus p prime 2 sine phi for the electron. So we have p prime 2 cosine phi, that is equal to h nu over c minus h nu prime over c cosine theta, and p prime 2 sine phi, that is equal to minus h nu prime over c sine theta. So you see here we have the sine of phi, and we have the cosine of phi, and we have the sine of theta and cosine of theta. So we can calculate the tangent of these angles. So tangent phi, if you divide this equation by this equation, you get tangent phi that is equal to minus h nu prime over c sine theta over h nu over c minus h nu prime over c cosine theta. So you can simplify by an h over c. So minus nu prime sine theta over nu minus nu prime cosine theta. And you can multiply by a minus, so you get nu prime sine theta over nu prime cosine theta minus nu is equal to, you can even divide by nu prime, so it's sine theta over cosine theta minus nu over nu prime. Okay, so tangent phi is equal to sine theta over cosine theta minus nu over nu prime. you see, and you know that nu is bigger than nu prime, so this quantity is less than 1. Sorry, this quantity is bigger than 1, because nu is greater than nu prime, so this quantity is greater than 1, and cosine is less than 1, so the denominator is always negative. So tangent phi is always negative. So phi goes from minus pi over 2 to 0. So electrons are always ejected forward to the front, forward in this quadrant, only in this quadrant, not upwards, not backwards, only in this part that is highlighted by the green color. Okay, so we only have electrons in this part of the space. Okay, so we are always in an elastic collision. We will see the relation between between the angles of ejection. So it's an elastic collision, so 1 plus 2 gives you 1 prime plus 2 prime. And you know that the scalar product of 2,4 vectors is always invariant. So let us consider a new quantity. Let's take the quantity P minus P prime for any particle. So it's either for 1 or for 2. You consider the quantity P minus P prime. And you multiply this quantity by the 4 velocity of R star. The 4 velocity of R star is the velocity of R star with respect to R, of course, which is the rest frame. So the 4 velocity of R star, we will call it U star. So the quantity P minus P prime times U star is the scalar product of 2,4 vectors, so it is invariant. So let's find this invariant in R star. We have U star and R star in the same frame. So the frame is at rest with respect to itself. So the spatial velocity is 0, and you have the time coordinate U0 star. And for a certain particle, P star is the 3D momentums along X, Y, and Z, and of course E star over C as a time coordinate. The same for P prime, for the same particle after collision, P prime star is equal to the 3D momentums along X, Y, and Z after collision, and the time coordinate that is E prime star over C. Okay, so we have the 4 coordinates. We can find the quantity P minus P prime U star. Of course, this is an invariant, so it is equal to P star minus P prime star times U star. And if you take it from these matrices representing the 4 momentums, so if you calculate P minus P prime, the space is always multiplied by 0, so we need to consider only time coordinates. So it's E star over C minus E prime star over C times U0 star. And we found previously that in R star, the particle conserves its energy. So the energy is invariant in R star for the same particle. So E star is equal to E prime star. So this entire same equation is equal to 0. So you always have P minus P prime times U star equals to 0. You can use it anywhere in any inertial frame, but only for elastic collision. This doesn't apply to to non-elastic collisions, only for elastic collisions. So let's take an example and apply this quantity to a certain elastic collision between an incident particle number 1 and a target particle number 2. So we have 1 hitting a number 2, particle number 2 that is initially at rest, and 2 becomes 2 prime because this is an elastic collision ejected at an angle theta 2. So let's find this angle. So before collision, I'm using the same slides as the French class. Okay, this is before collision. So P2, the initial particle number 2 is initially at rest, so it's 0, 0, 0 in space, and E2 over C, which is the rest energy, so it's M2C squared over C, it's M2C, and after collision, it's P prime 2, so it's P prime 2 cosine theta 2 along X, and P prime 2 sine theta 2 along Y, 0 along Z, and P prime 2 over C as a time coordinate. And U star is the velocity V of, or the speed V of R star with respect to R over the radical of 1 minus V squared over C squared, and the time coordinate that is usually 1 over the radical of 1 minus V squared over C squared. But since we are considering C, so we have a C here instead of 1. And V, you know, V is the sum of P's over the sum of E's times C squared. So it's P1, you can take it before collision, it's P1 over E1 plus the rest energy of E2, it's M2 C squared times C squared. Okay, so we have P minus P prime times U star. We begin by time coordinates minus space coordinates times minus space coordinates times U star. So it's times C over radical, then times V over radical because this is the X coordinate. And we replace V by its value. So E2 is the initial energy of 2, the rest energy, MC squared, and this is M2C squared. So we are applying the P minus P prime times U star on particle number 2. You can also apply it on particle number 1. Here in this example, we are applying it on particle number 2. So only we need the mass of 2. So M here is M of particle number 2. The rest energy E2 is MC squared, so over C minus E prime 2 over C, C over the radical, minus times minus is plus P prime 2 cosine theta 2 times 1 over the radical, and we replace V by its value, so it's PC squared over E1 plus E2, that is M2 C squared, that is equal to 0. So we can here simplify by a C, so it's MC squared minus E prime 2 times 1 over the radical plus P1 times P prime 2 cosine theta 2 C squared over the radical times E1 plus M2 C squared is equal to 0. And you make the common denominator and you take your numerator as equal to 0. So M C squared minus E prime 2 times P1 plus M2 C squared. This is the same M, okay? So it's M2 and M are the same mass of M2. Plus P1, P prime 2, C squared cosine theta 2 is equal to 0. So you can find the cosine of theta 2, which is this quantity. So it's just a manipulation of mathematical equations. There is not a lot of physics here, so just you work out your equations. Okay, so now we move to non-elastic collisions. So non-elastic collisions, by definition, is a collision where we have different particles after collision. So if you take a collision between particle 1 and a particle 2, then after collision you have completely different particles such as 3, 4, and maybe 3, 4, and 5, etc. So here we have a creation of particles, a non-conservation of the masses. We have different particles after collisions and before collision. This is by definition a non-elastic collision. So we have different particles, the mass is not conserved. So these non-elastic collisions have a threshold. The threshold is defined to be the minimal energy of the incident particle, and here it's the kinetic energy. So it's the minimal kinetic energy of the incident particle in order to be able to produce this high energy non-elastic collision. Because here you are creating new particles, so you need a minimum of energy. This minimum of energy is called the threshold of a collision. So let's find this threshold. We are working in our star, so P star is the momentum, the total momentum before collision is the sum of momentums in our star, which is equal to 0, because in our stars the sum of all 3D momentums is 0, and the total energy is the sum of EI star over C, so it's the total energy E star over C. Of course, the energy is conserved, so you can calculate it before or after collision, it doesn't matter. In R, we have the sum of 3D momentum, so the total momentum is the sum of 3D momentums, which is the total 3D momentum, and the sum of energies over the C, which is over C, which is the total energy over C. So, okay, we need invariance. You know that scalar products of 4 vectors are invariants. The same applies to the square of the momentum, the 4 momentums. So P squared should be equal to P star squared because it's an invariant quantity. So P squared here is P squared here is E squared over C squared minus P squared, and P star squared is equal to E star squared over C squared. So we multiply this equation by C squared and we get E star squared that is equal to E squared minus P squared C squared. So we only have squared quantities, so everything is positive here. So you see that E star squared is less than E squared because it's E squared minus a positive quantity. So E star squared is less or equal maybe at the limit than E squared. So in R star, this is a condition that you can always consider in R star. The energy is minimal in R star, the total energy, not for a specific particle. The total energy, when you calculate the energy, it is a minimum in R star. So the energy is minimal in R star. It is conserved before and after collision in R star, but if you compare the energies or the energy in R star and in R, you will find that the energy, the total energy in R star is less than the total energy in R. Okay, but for the same frame, it is conserved before and after collision. So let's consider an example. Our example is the production of a proton-antiproton pair. So here we have a collision between two protons. If you make this collision at low energies, so if you collide two protons, you will end up by having two protons after collision with different momentums, but it would be an elastic collision. When you make it at a high energy, this collision between two protons will produce four protons, P plus a pair, P plus P minus. P minus is the anti-proton, so it has the same mass but an opposite charge. So as you know, the mass of a proton is 938 mega electron volt over c squared. So let's find the threshold energy of this equation, or the minimum kinetic energy of incident P in order to produce this extra pair of proton and antiproton. Of course, proton and antiproton will annihilate almost instantaneously and become photons or pure energy. Okay, so the total P is the total 3D P and the total energy over C as the time coordinate, and P star, you know, the sum of 3D P's in R star is 0, and the total energy is E star over C. And we already know that E star squared is equal to E squared minus P squared C squared. So the initial energy, or the energy in R, if you calculate it before collision, it's the same after collision, but you can easily find it before collision. It's the kinetic energy of the incident proton plus the rest energy of the two protons, so 2mc squared. So it's the kinetic energy T plus 2mc squared minus P squared C squared. Okay, so let's now consider only the incident photon. For the incident photon, let's call it proton number 1. The momentum, the 4 momentum P1 is formed by the 3D momentum P1 plus the time coordinate E1 over C. And E1, you know, E1 is the kinetic energy of this incident photon plus its rest energy mc squared. Or you know that P squared for any particle is equal to m squared C squared. So if you calculate P squared is E1 squared over C squared minus P1 squared, that is equal to m squared C squared. So we replace E1 by its value. So T plus mc squared over C squared minus P1 squared is equal to m squared C squared. And you multiply this equation by C squared, so P1 squared C squared is equal to T plus mc squared minus m squared C to the power 4. And you develop this equation, T squared plus m squared C4 plus 2T mc squared minus m squared C squared. So you remove m squared C4 and you get T squared plus 2T mc squared. So this P squared C squared is equal to T times, T is a common factor, so it's T times T plus 2 mc squared. And we replace the P squared, C squared in the equation of E star. So E star squared is equal to T plus 2mc squared minus P1 squared C squared, which is the same P squared C squared as T times T plus 2mc squared. You develop this equation, T squared plus 4m squared C4 plus 4mc squared T minus T squared minus 2mc squared T, you remove the T squared and you get 4m squared C4, and here you have 4 minus 2, it's 2mc squared T. Okay, you have a common factor that is 2mc squared times 2mc squared plus T. So E star is the radical of this quantity. So it's 2mc squared times 2mc squared plus T to the power half. Okay, this is E star, and you know that the energy in R star is the minimal energy, the minimal value of energy. Okay, this minimal value of energy should be at least equal or greater than the rest energy of the product after collision. Because after collision, you have 4 protons, proton 1 and proton 2 plus the pair proton and antiproton. So you have a combination of 4 protons after collision. So this minimal energy should be at least equal to the rest energies of these 4 protons, to the sum of the rest energies of these protons. So E star should be equal or should be greater or equal than 4mc squared. And E star is equal to 2, let's make it squared. Let's make it squared instead of taking the radical. So 2mc squared times 2mc squared plus T is greater than 16m squared C4. And you do the calculation and you find that the threshold or the kinetic energy T of the incident proton should be greater than 6mc squared. So your threshold is 6mc squared. So that is 6 times 938 mega electron volt over C squared times C squared. So you need an energy of about 5.6 giga electron volts in order to have this non-elastic collision and to produce the pair of proton and antiproton. Okay, so I will end this chapter by explaining some collisions or some annihilation reactions. So annihilation, when you have 2 particles, 1 and 2, that become 1 particle, let's say particle number 3. So you have 2 particles fusing or annihilating or fusing into 1 particle. On this first example, we will consider that at least one of the initial masses, 1 or 2, at least one of them is different from Z. So let's see if M3 is different from Z. So conservation of momentum, P1 plus P2 is equal to P3. So P1 plus P2 squared is equal to P3 squared. And P3 squared is, of course, is equal to M3 squared C squared, which is an invariant. And in R star, if you consider the same invariant in R star, because P1 plus P2 squared, here we should have S squared here. So P1 plus P2 squared is equal to P1 star plus P2 star squared, which is invariant. So P1 star is the little P1 star in space and E1 star over C. The 4P2 star is the little P2 star and E2 star over C. So P1 plus P2 star, P1 star plus P2 star is the sum of little p's, which is equal to 0 in R star, and the sum of energies E1 star plus E2 star over C. Okay, so if we consider this square, P1 star plus P2 star squared is equal to E1 star plus E2 star over C squared, and the same that is equal to M3 squared C squared. So you can multiply or just put the C squared here. So E1 star plus E2 star squared is equal to M3 squared C4. So obviously you have energies, otherwise you don't have particles. So if you have your initial particles and you have your initial energy, so this quantity is different from 0, and C4 is of course different from 0. So M3 should be different from 0. And even if M1 is equal to M2 is equal to 0, so collisions between photons, neutrinos, any massless particles. So we repeat the same calculations, but here we are considering random directions, not along X, not along Y, any random directions. So the little P1 vector is equal to E1C in magnitude, but the coordinate is E1 over C times the unit vector in whatever the direction. So the unit vector is the vector divided by the norm. So it's P1 vector over P1. And the time coordinate is E1 over C. The same for P2, which has a magnitude of E2 over C. So the 4P2 is E2 over C times the unit vector, which is little P2 vector over P2, and E2 over C as a time coordinate. So if you take P1 plus P2 squared, which is P1 squared plus P2 squared plus 2P1 P2, that is equal to P3 squared, so M3 squared C squared. Then P1 squared for massless particles is equal to 0. P2, if it is massless, so it is 0. So 2 times P1, P2, you use these for vectors. So the time coordinates E1, E2 over C squared minus E1 over C times E2 over C, P1 vector, P2 vector over P1 over P2. That is equal to M3 squared C squared. So it's 2E1, you can multiply by C squared. So you have 2E1, E2 as a common factor, 1 minus. So the product of these vectors over the norm is just the cosine between the two unit vectors. So it's 1 minus cosine theta, that is equal to M3 squared C4. So if theta is different from 0, so if the two photons are not parallel, so in any type of collision, when theta is different from 0, this equation cannot be 0, because cosine theta is always less than 1. So M3 should be different from 0. Okay, this is the end of this chapter. Next time we will do some exercises. Okay, see you next time.